All right, thanks, you 12s. Yeah, so looking at our study design, here's all the different functional groups that we should be able to recognize. Remember, we don't have to name them all, but we do need to recognize alkanes, kenes, kynes, benzene, haloalkanes, primary amines, primary amides, alcohols, aldehydes, ketones, carboxylic acids, and non-branched esters. So let's go through them of what the IR spectras will look like for each of these functional groups. Alkanes, kenes, and kynes will be more or less the same. Yeah, they're pretty much less than the 1500 region. We are going to see a peak around the 1500 mark. That's going to be weak and narrow if an alkene, corresponding to the carbon-to-carbon double bond. Carbon-to-carbon triple bond occurs around 2300, but you'll notice from the data book, thanks, Leo. From the data book, alkynes don't appear in the data book. So you will therefore deduce that we're not going to see an alkyne in a spectroscopic question. And every molecule that we look at is going to have a C to H stretch in that 2900 mark. Yeah? Yeah. Yes. Yeah. Okay. Sure. Let's just share. Let's look at our next one. Haloalkanes will look much the same. Fingerprint region, going to have something around 800. Yes, there's going to be other noise present, but if you are given a haloalkane in a question, the carbon to chlorine or carbon to bromine bond will be labelled. Okay? So if it's a haloalkane, they will label the carbon to halogen stretch. Cool. And then you're going to have other noise here, so I'm ignoring the other noise for now. But yeah, and then what's this corresponding to? C to H stretch, narrow, right? In that 2900 to 3000 mark. You might see a couple of little tiny dips and stuff like that, but mainly it's going to be one peak. Okay, let's look at amine now. Amine, obviously our RNH2. We're going to see our C to H stretch, narrow. We're going to see an N to H stretch. Remember, N to H is reasonably narrow, 33 to 3500. So we're going to see very little overlap between these two peaks. Yeah, so two distinct peaks, both of which are rather narrow. How that's different to an amide is the amide obviously has the C double bond O stretch as well. Okay? So C to H, N to H, two separate peaks, and the C double bond O. C double bond O, always around that 1680 to 1700 mark. It's always strong and it's narrow. So it's narrow, strong in intensity, and around that 1700 mark. Yeah? Okay. Now let's look at alcohols. Alcohols will look similar to an amine, but the O to H alcohol stretch we know is slightly lower. Yeah? Slightly lower. And so what we often find, we still see two distinct peaks, but there's that little bit of overlap. Yeah? So there's a bit more separation in an amine and an amide, right, because of the narrowness of the N to H stretch. Alcohol, two distinct peaks, one around that 3000 or 2900 to 3000, one around that, 32 to 3500 or 32 to 3600 mark. So this is a little bit broader than an N to H stretch. How that's different from a carboxylic acid is, as we talked about yesterday, that O to H acid stretch is very broad. So we see that really broad peak, which overlaps with the C to H stretch. Yeah? So the O to H is likely to be the first dip if we were to label that, O to H. And then we're going to see a little nick. Right? So imagine, I like to think of it, it looks a bit like a tongue. So imagine you've bitten your tongue, you've got a little nick in your tongue, right? And that corresponds to the C to H stretch. So it's broad. So two things we look out for in a carboxylic acid. Broad peak around that 25 to 3500 mark. And it must also have that 1700 C double bond O stretch. If we don't have both of those things, then it cannot be an acid. And it's unlikely we're going to see a broad peak without the presence of that C double bond O. Be careful, if I see a C double bond O and this doesn't appear to be as broad, if we see the two distinct peaks, yeah, so this isn't too distinct, is it? You see that? Little nick, not two distinct peaks. Two distinct peaks might be an alcohol and a ketone if we've got multiple functional groups present. Okay? So just keep that in mind. Lastly, our aldehydes, ketones, and non-branched esters are all going to be very similar. They're going to have that C double bond O stretch and a C to H stretch, and that's it. We might have a C to O stretch corresponding to the ester as well, but that's in the fingerprint region. So we're not expected to analyse peaks that are within the fingerprint region. So if I have a spectroscopic question and I'm looking, is it an aldehyde, a ketone, or an ester? I need to use other spectroscopic techniques to deduce what that might be. Yeah? You're going to be given the other spectrograms, right? So like with mass spec, in one of the worksheets, is you've got two possible structures. And you were asked to analyse, so the worksheet I provided you last time, when we talked about mass spec, we had two different structures, and it said which of these structures corresponds to, right, that given mass spec. Both of them had the same, I think they were both ketones from memory. Both ketones. One had the C double bond O in the middle, so pentane backbone, ketone in the middle. One had the ketone to one side. Yeah? And we looked at the different fragmentations of what that looks like. So we can use that to deduce one ketone from another. In this, we go, right, oh, that might be a ketone, or it might be an aldehyde. Right, now I'm going to look at the mass spec, or the NMR, to deduce what that actually will look like. When we start to look at NMR next week, right, you can get a lot of information from NMR, proton NMR in particular. All right. So any questions on that?